And I want to introduce our today's speaker, Eugene Ferapontov from the Loughborough University. And I hope you see, he will speak about quasi-linear system of Jordan block type. Zhenya, you are welcome. I ask everyone to, except for Zhenya, to mute your microphones.
Thank you very much, Joseph. It's always a great pleasure to attend your seminar. So today we'll speak about several simple properties of systems of Jordan block type. And this is based on 3 joint papers on joint work with Maxim Pavlov, Lin Xue, and Pierre-André Vergala. So here is the plan of my talk. Can you see the screen yet? Okay, so this is the plan of my talk. Please let me know if something goes wrong. So I will start with a reminder on diagonalizable systems of hydrodynamic type. This is something very well understood, right? And then I will move on to systems of Jordan block type. The first thing is I will mention a relation of integrable systems of Jordan block type with the modified KP hierarchy. In a sense, integrable hierarchies of Jordan block type are governed by MKP hierarchy. And this is based on our paper with Lin Xue, with this one, the first paper here. Then I will discuss a linear degeneracy of Hamiltonian systems of Jordan block type. So it turns out that a system of Jordan block type, if a system of Jordan block type is Hamiltonian, then necessarily it must be linearly degenerate. This is a new phenomenon. It's not there for diagonalizable systems, right? So there is a strong constraint appearing in the Jordan block case. This is based on our preprint with Pierre-André Vergala. And then I will discuss a meaningful example where systems of Jordan block type appear, namely delta functional reductions of the kinetic equation for solid on gas. Okay, so let me start with diagonalizable systems of hydrodynamic type. This is something well known, and I'll summarize all this in one slide. So just this slide contains everything I need. So diagonalizable systems in Riemann invariants are equations of this form. So VIs of R are, so the matrix of such system is diagonal with eigenvalues V1 up to Vn. I takes values from 1 to n. So VIs are, okay, the eigenvalues of the system, or they're called characteristic speeds. All right. Systems of this diagonalizable form appear in many applications, and the necessary condition for diagonalizability, necessary and sufficient condition for diagonalizability in the semi-simple case is the vanishing of the Heintius tensor of a system. I'm not writing this down. It's something well known, and I don't want to stop on this in more detail. So there is an invariant criterion for reducibility of quasi-linear systems to this form. In the case, the matrix of the system is semi-simple. Okay, for diagonal systems, commuting flows are also diagonal, but they have different eigenvalues, different characteristic speeds, WIs, and the commutativity condition between these two systems is written down here. So in this, they look symmetric, these commutativity conditions, they look symmetric in V and W, because it's a symmetric condition that two systems are compatible. This is equivalent to the requirement that Ri T tau equals Ri tau T, mixed derivatives commute. So Ri's exist as functions of 3 variables, x, t, and tau. All right, so let me rewrite these equations in a slightly different non-symmetric form. I will think of these VIs as given, right? And W's as something that we seek, right? W's are unknown, VIs are given. So then I will rewrite this system, these equations like this. First of all, I will call this expression on the right-hand side just Aij. So Aij is this thing. then this system can be written as djwi equals aij, this expression, times this denominator, wj minus wi. So I get this linear system for w's. So, okay, vi's are given. This means that these coefficients aij's are given to me. And to find commuting flows, I have to solve this linear system. All right? This linear system is overdetermined, and it must be compatible. So integrability conditions are the compatibility conditions of this linear system. And these compatibility conditions are equations for aij's, and they're written down here. Right?
Zhenya, I'm sorry, why 2 + 1 dimensional?
Okay, it looks like n-dimensional, right?
Yes.
But in fact, you see, for aij's, all derivatives in k variables where k is not equal to ij are given, but derivatives in ij variables are not given, right? Therefore, Gursa data for such system is a function of two variables. You can define aij as a function on the ij plane, coordinate plane. Right, so Cauchy data, so Gursa data for such system involve functions of two variables only. So it's actually two-dimensional system, right? Well, although it looks n-dimensional, but it's 2 + 1, strictly speaking. And this system for aij is actually equivalent to 2 + 1 dimensional and wave system, right? So let me then. So these equations, let me kind of summarize the construction of this integrable hierarchy, commutative hierarchy, in a slightly different way. So as follows, you take an arbitrary solution, aij, of these n-wave equations, right? And you fix this solution, right? This is fixed for the hierarchy. And then for this fixed value of aij, right, you solve this system, this linear system, and different solutions of these equations, of these linear equations, provide you different commuting flows of the hierarchy. So in other words, you fix solution of this system and you vary solution of this system, of this linear system, which is a Lux pair for the n-wave equations. So these equations for W can be viewed as Lux pair, as Lux equations, linear Lux equations for this system. So in other words, to construct diagonalizable hierarchy, I fix potentials aij in the n-wave system, and I vary the Lux pair, the solution of the Lux pair. And this gives me the whole commuting hierarchy. We will see that the same picture holds for systems of Jordan block type. But the hierarchy is different and the Lux pair is different, but the rest is more or less similar. All right. Okay, let me move on to systems of Jordan block type. These are equations of this kind, where the matrix of the system has this upper triangular Toeplitz type. So what means Toeplitz? Toeplitz means that elements along this diagonal are the same, elements along the next diagonal are the same, and so on. Here I'm giving you an example of a 3x3 Toeplitz system, but n by n is similar. Right, so what is important about systems of this form? That for any, by the way, this V1, V2, V3 are functions of R1, R2, R3. These are functions, of R1, R2, R3. These R's are kind of analogs of Riemann invariants, right? So it's a canonical form of system of Toeplitz type, of Jordan block type. Clearly, this matrix has only one eigenvalue, namely V1, which appears here on the diagonal. That's the only eigenvalue of this system, right? And this matrix has the type of a single Jordan block, right? What is important about such systems is that their Hantjes tensor is identically zero, like in the diagonalizable case, right? For any V's, for any of these V1, V2, V3, the Hantjes tensor of any such matrix is identically zero. right? In for arbitrary n, of course, it's I'm just writing it for n equals 3 for clarity. So what? Okay, what are commuting floors with such system? So I claim that commuting floors has the same upper triangular choplet structure, but of course this V1, V2, V3 will be different, right? But they will have the same choplet structure. One can also consider block diagonal systems, quasi-linear systems, where each block has this kind of choplet structure. This is the most general case for which integrability theory can be constructed, right? So systems which have this kind of choplets blocks on the diagram. But for a moment, let me deal with a single choplets block. Okay, so we say that a system of this kind is integrable if it possesses infinitely many commuting floors of the same choplets type, right? Where do such systems occur? So first of all, why they were not considered before? So the theory of the diagonalizable systems of hydrodynamic type, integrability theory of such systems, dates back to the paper by Dubrovin and Novikov. I think it dates back to the 1983, and then it was developed by Sergei Tsarev in his PhD thesis. Dubrovin, Novikov, and Tsarev, they were motivated by a meaningful example of Witham equations. So Witham averaged equations, they are semi-simple and they're reducible to Riemann invariants. So there were many meaningful examples of such systems coming from physical applications. And there were no examples of Jordan block type coming from meaningful applications. So such systems were simply not studied, they were not of interest. But they recently appeared in applications, in particular as hydrodynamic reductions of multidimensional dispersion-less integrable systems. Like, for instance, a linearly degenerate, Pavlov or Mikhailov equations, heavenly type equations. So hydrodynamic reductions, one can look for hydrodynamic reductions in choplets form. And there are such reductions, right? Then systems of this type appear in the theory of Frobenius manifolds, non-semi-simple Frobenius manifolds, when the product, associative product, is not semi-simple. Then principal hierarchies of the corresponding Frobenius manifolds, they are of this type. And there are some papers on such Frobenius manifolds by Paolo Lorenzoni and Sara Perletti, quite recent papers. And also equations of choplets type appear as delta functional reductions of the kinetic equation for solid on gas. I will discuss this example at the end of my talk. This will be actually my main example. For kinetic equation for solid on gas, their delta functional reductions is a quasi-linear system which splits into, which has block diagonal structure, and each block is a 2x2 choplets block of this kind, right? Okay, now let me show you examples of commuting systems of this kind. First, I will start with the 2x2 case. It's very simple, right? So these are the equations. Psi is some function of R1, R2. Psi1 means derivative by R1, d psi by dr1, right? Clearly, this is a choplets type system, Jordan block type, right? And this psi is not arbitrary. This psi function psi, it satisfies this linear system. This linear system. Psi2 means d psi by dr2, derivative by this thing. Psi11 means second order derivative by r1. Psi1, first order derivative by r1. And this 2w1 is just a potential, some potential, right? W is some function. Why I'm using this funny notation for this potential, like 2w1, rather than calling this just, okay, v or something. I call it 2w1 because in this form it will appear in more general case later, right? Still, you can think of this as just any given function, right? 2W1 is just any given function. But for convenience, I write it as 2W1. So how to construct systems of this form? You fix this potential 2W1, just arbitrary function, right? Arbitrary function. And you take arbitrary solutions of this linear equation, linear PDE. It's like heat type equation. You take arbitrary solutions of this PDE and you put them here. So I claim that you fix W1 and vary psi, you get commuting flows, right? So it's the same picture as for diagonalizable systems. You fix potential of an integrable PDE and you vary equations of the Lux pair. Sorry, vary solutions to the Lux pair. And then you get commuting hierarchy. So maybe it will become more convincing for in the 3x3 case. At least connection with the MKP hierarchy will become more clear. Here, what is the connection to MKP hierarchy in this two-component case? It's via this equation, because this equation is Lux equation for the MKP hierarchy, for the modified KP hierarchy. So I repeat that we fix W and vary psi, and then we obtain all commuting flows. All right. So let's look at the three-component case, which is much more convincing. So here I'm writing a three-component Toeplitz type system. So you see on the diagonal, on the main diagonal, you have psi. All right. On the next diagonal, you have psi1, psi1. Right? And then in the upper right corner, you have this expression, psi11 plus W1 psi1. All low indices are derivatives by R1, R2, R3. So index 1 means we differentiate d psi by dr1. All right? So now what is W? W is a solution to this PDE. It's the MKP equation. Modified KP equation. It has three independent variables, R1, R2, and R3. Right? So it's equation in three independent variables. It's a single scalar equation. This is an integrable PDE.
Yeah. I'm sorry. Do I understand correctly that this MKP is the condition for the flows to commute, yes?
And eventually, yes.
Eventually, yes.
Yes, I'm just telling you the construction. It's not how it was obtained.
Okay.
I'll explain you the construction and then I'll say a few words. First of all, how to obtain commuting systems of Toeplitz type. Okay, you take this MKP equation, right? And you fix any solution W, right? Just fix any solution, right? Then this equation has the Lux pair in terms of linear system in terms of psi function. So first Lux equation and second Lux equation, right? This is the Lux pair for MKP. So what you do, you fix W, fix solution of this, and then you vary solutions to the Lux pair. You take all possible solutions to the Lux pair, psi's, right? Fix W and vary psi. And you put these psi's here, right? You have many different psi's. For a given W, you have many solutions to the Lux pair, right? Because it's just a pair of compatible linear PDEs. They have many solutions. So if you fix W and vary psi's, you get commuting hydrodynamic systems. Right? So how this was obtained? So we just took two Toeplitz systems with lin-lin. We took two Toeplitz systems, we commuted them. Then we wrote commutativity conditions, simplified them. And then we realized that what is coming out is reminiscent of a 2+1 dimensional hierarchy. And then we identified this DKP hierarchy. So it was just by direct calculation. What we started with are just two Toeplitz systems, we commuted them and then reduced commutativity conditions to this kind of form, right? Matrices to this form, right? So generic commuting hierarchy of Toeplitz type, three-component hierarchy, is represented by this formula, right? So if you if you look at the upper left corner, this corner of this matrix, right, then you recognize the system that we had before, this one, yeah? And this continues, right? It turns out that in a similar way, I can write 4-component systems of Toeplitz type. They will always have psi on the diagonal. Then on the next diagonal, there will be psi1. Then on the next diagonal, there will be this element. And then on top, there will be an extra element, which is more complicated. I'm not showing it now, right? So this thing generalizes to the n-component case. This is what I want to say, right? So in other words, integrable hierarchies of Jordan block type are governed by the MKP hierarchies, MKP hierarchy. So diagonalizable equations of hydrodynamic type are governed by the n-wave hierarchy. And Toeplitz and Jordan type commuting hierarchy is governed by the MKP hierarchy, right? Different hierarchies. So what do we have in general? If you take a quasi-linear system which consists of several Toeplitz blocks, then we have a sort of a merging of n-wave hierarchy with MKP hierarchy. So like several MKP hierarchies which are coupled according to n-wave hierarchy. But we haven't explored this in detail, right? But this is what will be the general picture. All right. Then let me move on to the Hamiltonian property of such systems. Okay, let me remind you the general setup for Hamiltonian equations. So let me take an arbitrary quasi-linear system. An arbitrary quasi-linear system. So here Vij is some matrix. It can be diagonal matrix. Then I have what I showed on the first slide, semi-simple quasi-linear systems. Or for Vij, I can take an upper triangular Toeplitz system. So this will be Jordan type system, but it can be any matrix. All right, what does it mean that such system is Hamiltonian? So it means that it can be written in this form: Aij, some differential operator applied to variational derivative of some conserved density, of some conservation law. And here for Aij, we take an operator of Dubrovin-Novikov type. This is all well known. And for H, for the Hamiltonian, we take a Hamiltonian of conserved density of hydrodynamic type. So the density which depends on R's only, not on the derivatives. All right. Here, Jij is a metric, is a flat metric, and Bijk are Christoffel symbols with one in the contravariant Christoffel symbols. Right. So this is all well known. Operators of this form were classified by Dubrovin and Novikov, and this Hamiltonian formalism was thoroughly studied by Sergei Tsarev, and he proved he derived the following equations. So for this matrix Vij to be Hamiltonian, to appear from this setup, the following conditions must be satisfied. This matrix Vij and this metric G must satisfy the following equations: the first set of equations and the second set of equations. Here, nabla denotes differentiation in the Levi-Civita connection of the metric. Right here, I'm using metric with upper indices, right? This one, which appears in the Hamiltonian operator, and the metric with lower indices, which appears here. So one is the inverse of the other, right, as usual. Metric with low indices is the inverse of metric with upper indices. This is contravariant, this is covariant, right? And these are called Kadazzi equations for the matrix V. So in other words, a system of this form is Hamiltonian if the matrix Vij is the Kadazzi tensor, is a Kadazzi tensor in some flat metric, Gij, right? Okay, so it turns out that these equations imply a very simple constraint in the Jordan block case. Namely, a Hamiltonian system of a single Jordan block type, Toeplitz block type, is if it is Hamiltonian, then it must be linearly degenerate. It means its diagonal entry, V1, doesn't depend on the first coordinate R1. dV1 by dR1 equals 0. Let me bring you back to the general formula. So you see this V1 is the diagonal entry, is the eigenvalue of this matrix, and this V1 must not depend on R1, right? This is constraint coming from Tsarev's conditions. I want to emphasize that nothing like this exists for diagonalizable systems. This is peculiarity of Jordan block systems entirely, right? It's a very simple necessary condition, right? Systems of Jordan block type, and this condition is called linear degeneracy, right? This I will explain in the next slide, right? So systems of this form with this property are called linearly degenerate. So Hamiltonian system of Jordan block type must be linearly degenerate. This condition is necessary, but of course it is not sufficient, right? It's a very simple necessary condition. So now a few words about linear degeneracy in general. When do we call a system of a quasi-linear system like this linearly degenerate? Right here, Vij is some matrix. So we call this system linearly degenerate if eigenvalues of this matrix are constant, if derivatives of the eigenvalues of this matrix are constant along the corresponding eigenvectors. So every matrix has eigenvalues and eigenvectors, and we can calculate Lie derivative of every eigenvalue of this matrix along its corresponding eigenvector, right? If all such derivatives are zero, the system is called linearly degenerate, all right? So in particular, for diagonalizable systems, we have n distinct eigenvalues, and the corresponding linear degeneracy conditions just reduced to these simple equations. dvi by dri is 0 for every I, right? So V1 doesn't depend on R1, V2 doesn't depend on R2, and so on, right? Because d by dr1 is the eigenvalue corresponding to V1, right? And so we have these n equations. They are well-known conditions of linear degeneracy. Now, for Jordan block systems, we have only one eigenvalue, namely V1, and we have only one single eigenvector. It corresponds to d by dr1. So linear degeneracy conditions reduce to just this single equation. So this is linear degeneracy for Toeplitz type systems, right? If we have a system consisting of several Toeplitz blocks, then every Toeplitz block must be linearly degenerate. So its eigenvalue must be 0 along the corresponding derivative and the corresponding eigenvector, which is single for every Jordan block, right? Okay, so in other words, one condition for every Jordan block. By the way, let me return back to this kind of systems, to these systems, right? To general systems of Jordan block type. When we just derived this kind of equations, we started, of course, we asked ourselves a question about their Hamiltonian property. Are such systems Hamiltonian, right? And we always were getting kind of negative answers, right? And I couldn't believe. I thought we are doing a mistake. We are making a mistake in calculations, a typo or something, because I couldn't believe these equations are not Hamiltonian. But then you see, then we got this linear degeneracy constraint. What does it mean in this setting? It means that psi, this eigenvalue, which is psi, doesn't depend on R1. So d psi by dr1 is 0. But if d psi by dr1 is 0, this is 0, this is 0, d psi by dr2 is 0, d psi by dr3 is 0, everything trivializes. So these generic systems of Jordan block type are not Hamiltonian, right? They're just not Hamiltonian. These systems that are Hamiltonian, they form a special kind of stratum, like degenerate stratum. They're not generic. They correspond to systems where psi doesn't depend on R1, and such systems are not described by MKP hierarchy, right? It's a different class of systems. All right. So maybe one last comment on linear degeneracy conditions. Suppose we are given a system in this form, how to verify whether it's linearly degenerate. So you do the following. For this matrix V, right, you calculate its characteristic polynomial. So you calculate determinant lambda times identity matrix minus V, and you write it as a polynomial, right? F1, F2, Fn, these are coefficients of the characteristic polynomial. For each of these coefficients, yeah, you calculate its gradient. Gradient as a row vector, like df by dr1, df by drn. This you calculate for each of these coefficients of the characteristic polynomial. And then you verify this identity. You verify this identity. Gradient of f1 multiplied by the matrix of the system to the power n minus 1, plus gradient of f2 times v to the power n minus 2, plus so on, right? If this is 0, this thing is 0 if and only if the system is linearly degenerate. This is kind of an invariant condition of linear degeneracy. If you apply this condition to diagonal systems, you get this, right? If you apply this condition to systems of Toeplitz type, you get this, right? So, and you can apply it in general to any system. All right. So let me summarize. I'm now coming to example, meaningful example, reductions of solid gas equations. So what are the main conclusions so far? Two conclusions. First of all, systems of Toeplitz type, integrable systems of Toeplitz type, are governed by the MKP hierarchy in such a way that you fix solution to the MKP equation and you vary solutions to the corresponding Lux pair. In this way, you get all commuting systems of Toeplitz type. These systems are not Hamiltonian. Hamiltonian systems, they form a different subclass, quite elementary, I would say, elementary subclass, and they're linearly degenerate. So their eigenvalue must not depend on the R1. dV1 by dr1 is 0. These are two conclusions so far, right? And now I will describe a meaningful example of systems of Toeplitz type which are linearly degenerate, right? They are linearly degenerate, and they come from reductions of the soliton gas equations. Okay, let me try to describe this. So here is the kinetic equation for soliton gas. It's an integral differential equation for two functions. One is f, which is a function of eta, x, and t. X is coordinate, t is time, and eta, you can think of eta as a sort of spectral parameter, all right? You know, a soliton for, say, let's have in mind the KdV equation. Then each soliton, it depends, is a function of xt and the spectral parameter, discrete spectral parameter, eta. Each one soliton solution is described by these three quantities. It's a function of xt and the parameter. You can call it velocity, you can call it spectral parameter. And now you consider many solitons. You consider soliton gas, like a gas of solitons, randomly distributed. And f is kind of distribution function of these solitons. Each of s of eta xt is sort of transport velocity, right? And these two functions, f and s, they satisfy this continuity equation. This is the first equation. It's entirely differential, right? And also there is this integral differential equation, right? Here there are parameters. S of eta is just free soliton velocity, say KdV soliton velocity. And G of mu eta is this, so S of eta appears here. This S of eta, it doesn't depend on x and t. It depends only on eta. And this kernel G of mu eta, it's a kernel that appears here, right? It also doesn't depend on x and t. And this is a phase shift due to pairwise soliton collisions. It's a symmetric quantity. G of mu eta equals G of eta mu. So let me summarize again. You start with some integrable PDE, like KdV equation. Let's take Korteweg-de Vries equation. Then the soliton velocity is this thing, right? For eta squared, it's the lambda eta is the eigenvalue. For eta squared is the soliton velocity. G of mu eta is 2 soliton phase shift, right? These formulas come from KdV theory. Okay, once you have this S of eta and G of mu eta, 2 soliton phase shift, you can write down this system. But equally well, you can write this system, this integral differential equation, for an arbitrary integrable equation. You can take Sine-Gordon, you can take, Gardner equation, you can take nonlinear Schrödinger equation, you can take any integrable PDE. For every integrable PDE, you have solitons, they have their velocity, S of eta, this velocity will be different, and the interaction kernel, phase shift, to soliton phase shift, will be different function. These are formulas for KdV. For other PDEs, integral PDEs, these formulas, these functions will be different. All right, and so for every integrable PDE, you can form this kinetic equation for soliton gas. So what you are doing, you are considering many solitons randomly distributed for a given integrable system, right? Now, what can we say? And this system was derived by Gennadiel. It was a generalization of Zakharov's equation, kinetic equation, but sort of Zakharov's equation was uncoupled, and this is non-trivially coupled kinetic equation. All right. So there is a natural question appearing. We start with an integrable PDE, like KdV. Is this kinetic equation an integrable integral differential equation? So my original feeling was that it shouldn't be integrable for an arbitrary functions S of eta and kernel G of mu eta. Somehow this function and this kernel must be special, like for instance in the KdV case. This shouldn't be integrable for arbitrary S and mu, S and G. But all like evidence that we have so far, that we obtained so far, indicates that this integral differential equation should be called integrable, whatever this means. It's not clear what this means for equations of this kind, but it should be called integrable for arbitrary S and arbitrary G of mu eta. What we will do now, we will look for a special reduction of this kinetic equation, which will reduce this kinetic equation to a quasi-linear system, to a system of hydrodynamic type, which will depend on this S and this kernel G of mu eta. So they will explicitly enter the equations. And it turns out that this reduced system will be integrable for arbitrary S and arbitrary G, right? So at this step, we can't catch kind of these special values like in the KdV case. We do not get any constraints for S and G, which are parameters in this integral differential equation, right? They can be arbitrary functions. What is different is when we will require that the corresponding reduced system is Hamiltonian, we will get constraints for S and G, but this will come later, All right. So now I will impose delta functional reduction on this kinetic equation. Let's see what happens. Okay, delta functional reduction. So we will assume that this distribution function f of eta xt is the sum of delta functions, and s is just some continuous function. We will not assume anything about s. All right. So we will assume that this function f is the sum of delta functions, right? Ui of xt is the coefficient, and eta I is sort of, okay. So ui of xt and eta I of xt are parameters of this ansatz. And you plug this ansatz into the kinetic equation, right? And then when you plug this into integral differential, into this integral part, due to delta functions, all these integrals will be explicitly expressible. And then you plug it in here and you get, okay, you get the following system. I'm not going into detail here. This ansatz was originally, as far as I know, was proposed in this paper, joint paper by L. Kamchatnov, Pavlov, Zykov in 2011. But they considered a special case where this eta i's are constant, right? They looked at the case when eta i's are constant. And the general case was considered by Pavlov, Taranov, and L a bit later, and they considered a general case, right? And they derived the following equations. First of all, these functions ui's and eta i's, they satisfy a quasi-linear system of two n equations. We have n terms here, yeah, n terms like this. So we have n ui's and n eta i's, altogether 2n variables. And we get a 2n component system, right? This is the first set of equations. This is the second set, equations for u's, equations for etas. So we are happy with u's and etas because they appear here in this ansatz. But what are these? These are some extra variables. And it turns out that they can be recovered, these can be recovered from these equations. This is a linear system for these, right? This is a linear system. You see V appears here and these appear here, right? So it's a linear system. It's not a differential system. It's a linear, algebraic linear system for these, inhomogeneous. And it contains this S of eta i's soliton velocities. And we have this eta k i's, which are just two soliton phase shifts, right? G of eta k and eta I, right? So in other words, this soliton velocity and this phase shift, they appear explicitly in this linear system. So you solve these equations for these, and you get these equations, right? Explicitly in terms of u's and etas, right? But this form is inconvenient for me. What I want to show now is that this system can be reduced to n 2x2 Jordan blocks. It can be reduced to a block diagonal form where each block is like Choplett's 2x2 matrix. And this system will be linearly degenerate, right? Okay, and this reduction to Choplett's type is shown on the other slide. You see, it will probably be difficult to follow all these changes of variables. It doesn't really matter. If you wish, you can follow. I will just quickly show you how it works. So don't worry. You see, it's hard to follow all these changes of variables. But okay, let me still go through this. Okay, we have these equations for u and eta. These are found from this linear system, right? In terms of etas and u's, right? In terms of etas and u's. And I claim that this system can be reduced to n 2x2 Jordan blocks. This is shown in the next slide. Transformation to Jordan blocks. So what you do is the following. You introduce, instead of u's, you introduce new variables r's, which are given by this explicit formula, right? And this formula was found in the paper by Pavlov, Taranov, and L, 2012, right? So if you introduce r's by this explicit formula, right, then in the variables r's and etas, the system takes this form, right, this form. And you see for ri and eta I, what is written here is a 2x2 Toeplitz block, right? On the diagonal, you have this vi and vi, and above the main diagonal, you have this entry pi. So it's a 2x2 matrix, which have below the diagonal, we have 0. On the diagonal, we have vi, and above the diagonal, we have pi, 2x2 Jordan block, right? And there are n such Jordan blocks, all right? So what I need to show you is how to calculate these coefficients. What are VIs and what are PIs, right? What are the eigenvalues, VIs, and what are the terms above the diagonal, PIs, right? Okay, and this is, I'm showing you quickly the construction. You do the following. You introduce the following matrix, epsilon hat, n by n matrix. It's a symmetric matrix, epsilon hat, which has diagonal entries R1, Rn. On the diagonal, we have R1, Rn, right? And off diagonal entries are these epsilon ik, which is 2 soliton kernel. So here, and then you take its inverse minus the inverse of this matrix. Now, for n equals 2, what is this matrix epsilon hat? So you see on the diagonal, you have r's, r1, r2, and above the diagonal, you have this epsilon 1, 2. So it's a symmetric matrix. So it's sufficient to show what is above the diagonal, right? Epsilon 1, 2 is the same as here, right? Epsilon 1, 2 is this 2 soliton phase shift, right? So the matrix epsilon hat is this. And for n component, it's clear how to construct this matrix, and it's similar. And then you take its inverse, right? Minus its inverse. This you call beta hat. And for 2 component case, you get this matrix. This is matrix beta hat. And you introduce its matrix elements, you call them beta ik, beta ik. So this matrix, you see entries depend on R1, R2, and this eta 1, eta 2 in the 2 component case. In general, they depend on R's and etas. And then these expressions V's and P's are given explicitly by these formulas. You see, okay, I realize it, I understand it's impossible to follow all these changes of variables. It doesn't really matter. What matters is that such formulas exist. And you can efficiently work with these equations, right? VIs and PIs are certain explicitly known rational functions, right? And they depend on these epsilons, which are 2 soliton phase shifts. And they also depend on these functions, on soliton velocities. I introduce these functions. Psi k of eta k is the soliton velocity of eta k, at eigenvalue eta k, right? So, so this system involves these soliton velocities and involves these 2 soliton phase shifts and their derivatives, right? Okay. And it turns out that this system is integrable for arbitrary values of soliton velocities and arbitrary phase shifts, arbitrary functions of 2 variables, right? So there are no constraints on these functions. This system, I mean this system, yeah, it's integrable for arbitrary parameters. And what I will show in the next, I think 3 slides, I will show you the general solution to this system. Remarkably, this system can be even solved explicitly, not explicitly, implicitly, right? There is Tsaryov's generalized photograph formula, which applies to systems of Jordan block type, of Toeplitz type. And here it just gives you implicit solution in finite form, right? Which is quite remarkable for a rather complicated system. By the way, what is surprising? The system itself is quite tricky. These coefficients, VIs and PIs, are quite tricky. But the general solution to this system is absolutely elementary, as you will see on the next slide. It's really elementary. Then I will show you general commuting flows of these systems, of this system, and general conservation laws of this system. All can be calculated explicitly. This was done in our paper with Maxim. All right, let me start with the general solution. Right? Here I just copied the system. So these VIs, PIs, I repeat, there are certain functions of R's and etas, which depend on soliton velocities, and they depend on phase shifts, right? So here I wrote a general solution, how to understand these formulas. Okay, I need to explain what are these mu i's, first of all. What are these mu i's? Mu I of eta I are just arbitrary functions of one argument. So you have n functions of one argument, absolutely arbitrary. They appear here in the denominator, right? What are these psi I of eta I? These are soliton velocities. These functions we know, right? This is known to us. Okay, and this psi I prime, they're derivatives of these functions by the argument, right? So these coefficients we also know. I need to explain what are these phis. All right. These functions phi i's are defined by the following formulas. They are written here. Phi I differentiated by eta j, where j is not equal to I, equals this two-soliton interaction kernel times the function mu j of eta j, which is arbitrary. These are mu functions, arbitrary functions. All right. So I repeat, I take n arbitrary functions mu i's, right? I put them here in the denominator, and I put them here in the right-hand side. I multiply these functions by two soliton phase shifts, right? And then I reconstruct functions phi I from these equations, which are explicitly solvable, right? All compatibility conditions are satisfied, so trivially actually. So I can reconstruct this functions phi I. When I do this, I gain n functions of integration, because you see for phi i's, I have all j derivatives, where j is not equal to I. So I have one, for each phi I have one arbitrary function. So in total, I will have two n arbitrary functions. Okay, so now I explain what are phi i's. Okay, and then let's look at these equations. These equations, the last set of equations. Now we know psi i's are soliton velocities, phi i's we know, and now we reconstruct etas as functions of x and t. These are implicit relations. There are n implicit relations for etas as functions of x and t, right? In principle, we can solve for etas, right? And then we can reconstruct r's by this explicit formula. Once we know etas, we can reconstruct r's, right? I claim this is a general solution to these equations. They look, in my opinion, these equations are surprisingly simple. They're much simpler than the system itself. Coefficients of the system are really tricky, right? They're quite complicated ratios, rational functions, but these relations are really elementary, right? And this is quite surprising. Now, where these equations come from? They come from generalized Hodograph formula, and generalized Hodograph formula requires commuting flows. Commuting flows are shown on the next slide. Let me mention that on the next slide, you will see the same functions, mu i's, arbitrary functions of their variables and arbitrary functions, mu I of eta I, the same functions, and you will see the same functions phi i's, right? They will feature on the next slide, exactly the same functions. So, and they will parameterize generic commuting flows of my original system. Okay, let me show you the equations. These are general commuting flows. Here I copied the original system, right? So VI's and PI's we know. This is its general commuting flow. Tau is new time. Tau is time of the commuting flow. So these WI's and QI's are unknown at this stage. But as I said, commuting flows to a tuplet system must be themselves tuplets, right? This system is a collection of n 2 by 2 tuplets blocks, right? And the commuting flow is also a collection of n 2 by 2 tuplets blocks, right? What we don't know are these WI's and QI's. And here are the formulas. WI's are these, and QI's are these. Here, mu i's, in these formulas, what are the parameters? We have this mu i's, they are arbitrary functions as before, and phi i's are the same functions as before. They satisfy these equations, right? So the only parameters appearing in these formulas are mu i's and phi i's, right? So commuting flows depend on 2n arbitrary functions of n variable, as they should, right? So this confirms integrability of this reduced of this system, right? It possesses infinitely many commuting flows. Okay, now yeah, I have only 15 slides, so I have 2 more slides to go, right? So I hope I'll finish on time. This is what is Tsarev's generalized Hodograph formula. It's written here. Wi is x plus vit and qi is pit. This is Hodograph formula in the Jordan block case, right? So it turns out that if you take these expressions for pi, for wi and qi, for commuting flows, if you take vi's and pi's from here and put everything into this formula and simplify, then you get precisely these equations. So these formulas, I would like to stress that these formulas, when you put here wi's, vi's, qi's, pi's, they're huge, right? But they simplify dramatically and they become very, very simple, and they they give me a general solution. All right. Okay. Next slide will show general conservation law. Actually, it doesn't really matter. So, okay, I copied the system and I claim this system possesses infinitely many conservation laws of hydrodynamic type parameterized by 2n functions of one variable. So infinitely many. Again, this confirms integrability of my system, right? And these conservation laws, they also depend on arbitrary functions, but they're slightly different. They're not mu i's and eta i's as before. They're slightly different. These are just different functions. Sigma I of eta I and this tau I of eta I. These functions, sigma I are arbitrary functions, and then tau i's are these sigma i's times soliton velocities, right? So, okay, sigma i's and tau i's are arbitrary functions. No, sorry, tau i's are expressed in terms of sigma i's by this formula, so tau i's are not arbitrary. Sigmas are arbitrary, tau's are not arbitrary, and then you also introduce these functions psi i's by this formula. Okay, it doesn't matter. You have explicit formula for conservation laws. And then my final slide, it's about Hamiltonian aspects of this system.
Yes. The question concerning this slide. And
Okay.
all these conservation laws are pairwise independent.
Well, they are absolutely, they are linearly independent.
No, I mean cohomologically.
They are non-trivial independent, yeah. Like in the diagonal case, you have conservation laws parameterized by functions of one variable, right? In the diagonal case. And
Yes.
here they are parameterized by 2n functions of one variable, because it's 2n component system. But what is nice about this particular example, that these 2n arbitrary functions, they explicitly appear in this general formula. It's not just a general freedom, but they appear explicitly. You can solve linear system for conservation laws, right? Which always happens for linearly degenerate systems, in fact. Right? For linearly degenerate systems, you can find everything explicitly. Commuting flows, conservation laws, and for Jordan block systems, they're not an exception. It's the same, right?
Thank you.
Okay, now I'm coming to my last slide, but before I open it, I want to kind of motivate it. So, as I said, when I first looked at this else kinetic equation for soliton gas, it contains two parameters, soliton velocities and phase shifts, two soliton phase shifts. And my original kind of wish, I would say, was to find constraints for these soliton velocities and two phase shifts. I couldn't believe they can be arbitrary functions. I thought they must be constrained in some way, right? But you see, at least we did this reduction, hydrodynamic reduction. All these parameters entered this reduction, right? Soliton velocities, phase shifts, they entered this system. But still, it's integrable for arbitrary soliton velocities and arbitrary phase shifts. So integrability doesn't kind of isolate all these familiar soliton velocities and phase shifts for integrable PDEs like KdV, NLS, sine Gordon, and so on. Right? But what happens actually, that if you require Hamiltonian property of this system, then you do get constraints for these parameters, but they're too strong. For instance, KdV case doesn't appear. We get strong constraints. So let me show you what we get actually. By the way, since this system is linearly degenerate, this necessary condition for Hamiltonian property is satisfied. So the necessary sufficient condition holds, but it's not sufficient in general. So let me show you my last slide. We can look at, even starting from four-component case, the existence of a local Hamiltonian structure for this reduced system implies that this two-phase shift, namely this function g of eta 1, eta 2, has to be separable. It must satisfy this PD, which means that its generic solution is of this type, phi 1 of eta 1, phi 2 of eta 2, right? It's a generic solution. There are also degenerate solutions when this G is like this, a function of eta 1 only, or just a constant. All right, only in this case, this reduced system is Hamiltonian in the local sense. All right, and by the way, this condition of this was found by Pierandrea Vergallo. Right, he looked at Hamiltonian property of this equation, and he found this separability condition. And what is remarkable, to get this condition, you don't even need the flatness of the metric. It just comes from the first set of Tsarev's conditions. If you remember, I called them this, what are they called? Kadatsa equations, right? The first two set of Tsarev's equations. So you don't even need flatness of the metric. They come at an earlier level, I would say, these separability conditions. So in particular, KdV case is not locally Hamiltonian. Right, I do not know physical applications of this general case, but remarkably in the theory of kinetic equations for solid or gas, these last two cases are well known. the case C is called hard rod case, whatever it means, right? And the case B, this partially separable case, is called partially inhomogeneous hard rod case. So these are kind of known cases in the literature on this kinetic equation. But this case, as far as I know, it hasn't appeared explicitly. In these cases, we have explicit formulas for Hamiltonian structures. I'm not showing them here. They are not terribly complicated. They are explicit and very reasonable. I just don't want to load you with formulas. They exist. You can look at our paper with Pierre-André Vergal. Right, and moreover, these Hamiltonian structures, they're all compatible, and there are infinitely many of them. For any such interaction kernel, you have infinitely many Hamiltonian structures which depend on a certain number of arbitrary functions and a certain number of arbitrary constants. So it's a really quite, I would say, degenerate case. There are too many local Hamiltonian structures, which I personally don't like. So it's sort of a sign of certain triviality of the system. But on the other hand, the system has physical meaning. All right, so the main question is it possible to isolate non-trivial two-soliton phase shifts like KdV phase shift, NLS, Sine-Gordon phase shift by looking for non-local Hamiltonian structures of some kind? This is sort of work in progress, and but there is nothing to report at the moment. All right, so this is an open question, but I'm optimistic about this. I think that by imposing certain conditions on this Hamiltonian structure, non-locality of special type, you can catch this interesting two-phase interaction kernels, two-phase shifts. All right, so thank you very much.
Thank you, Zhenya. Very interesting. Questions, remarks?
May I ask a question?
Sure, sure.
Please name yourself.
The term linear degeneracy, the meaning looks similar to weak nonlinearity that was introduced by Rojdestvinsky.
It's the same. It's the same thing. You see, it's very unfortunate. Rojdestvinsky and Yanenko called it слабая нелинейность in Russian, right?
Exactly.
Which was transformed as weak nonlinearity. But in Western literature, Lux, for instance, Peter Lux, who studied systems of conservation laws, he calls such systems linearly degenerate. So this is called linear degeneracy in Western literature. And weak nonlinearity is something different. There are weakly nonlinear systems, but this means something different, right? So unfortunately, this is, what I call linear degeneracy is слабая нелинейность in Russian.
Okay, thank you.
Yeah, all right.
More questions? No. Well, Zhenya, thanks a lot. It was.
Thank you, Joseph. Yeah, thank you for
Yes, so we meet next Wednesday, and the speaker will be Sergei Dobrokhotov. You will receive the announcement. Goodbye. Thank you very much.
Thank you.